Welcome to Chapter 21 on the ISA of the simplified DLX. I'll explain what ISA stands for and what DLX stands for. So we have here two terms, ISA, Instruction Set Architecture, and DLX, which is a name of a simple microprocessor architecture. Now, if you look at the word architecture in the Collins Dictionary, you will see that architecture means the art of planning, designing, and constructing buildings. And in this chapter, we are interested in issues that are related to computer architecture. And the difference between the standard term architecture and computer architecture is that computer architecture refers to computers instead of buildings. So it is the art of planning, designing, and constructing computers. Now, computers are complicated. Even a very simple processor is built of tens of thousands of gates, and it is controlled by an operating system that has thousands of lines of instructions. So we're talking about very complicated systems. In order to deal with such complicated systems, good engineering practice is to use abstractions. And these abstractions are used by different people or different entities that are focusing on different aspects of this system. So, for example, a hardware designer is not interested in questions such as which programs will be executed by the computer. Now, this is a very important question if you're the architect, because if you're the architect and you want to know which programs will be executed, then that may dictate how much memory you need, how fast the memory needs to be, which types of instructions are common and need to be executed faster, and so on. So, different questions are interesting in different abstractions. Hardware designer doesn't care about which programs will be executed by the computer, but he has to provide a certain functionality of the hardware. The programmer, for example, doesn't necessarily even know what type of computer will be executing her programs. Okay? The architect, on the other hand, is supposed to be aware of the different aspects so that the design system, on one hand, meets the required price, and on the other hand, achieves the performance goals. So, we will need several abstractions in order to look and focus at different aspects of computer systems. And we will consider three main players, each of which has a different abstract view of the computer system. The first player is the C programmer, who writes programs, say in C or any high-level programming language. The user, who executes programs or applications. And the hardware designer. And of course, in this course, we are the hardware designers. Okay, so let's try to understand our players. The first player is the C programmer. The C programmer uses an abstraction in which the computer runs C programs, owns private memory, and has access to various peripheral devices such as a printer, a monitor, a keyboard, a mouse, etc. Supporting this abstraction in practice requires software tools such as an editor, a compiler, a linker, a loader, a debugger, etc. So this is the point of view of the C programmer. The computer can execute programs in C. The computer has access to memory, files, a monitor, a keyboard, etc. And of course, in reality, the computer cannot execute programs in C. And in reality, many programs are executed in some sense simultaneously. But when I'm the programmer, I'm thinking only about my program, and I pretend that the computer is completely dedicated for my needs, to to my needs. Okay, the second player that we want to talk about is the user. The user runs various applications, uses the abstraction of a computer that is capable of running several applications concurrently, supports a file system, responds to mouse movements, typing on the keyboard, etc. Supporting the user's abstraction requires an operating system to coordinate between several programs running in the same time and managing the file system. And of course, it requires the hardware that executes programs, but these programs are of course not in C. So this is the abstraction of the user. There's a computer. There are multiple applications which are being executed by the user simultaneously. These applications have access to files. They may display something on the monitor. They're influenced by the key presses on the keyboard. They require some memory. And all of these actions are coordinated, of course, by the operating system. Okay, so that's the user's point of view. What is the hardware designer's point of view? The hardware designer is given a specification called the instruction set architecture, in short ISA. The goal of the hardware designer is to design a circuit that implements this specification while minimizing cost and delay. So, what is happening here from the point of view of the hardware designer is that she's supposed to design hardware that executes programs written in machine language, and the outcome of these programs is of course stored in the memory. Okay, so maybe the memory is later connected to a display or whatnot, and you can see the outcome of the execution of the program on your monitor. Okay, maybe not absolutely necessary, but it is a possibility. The hardware designer is trying to design a circuit, a synchronous circuit that executes programs written in machine language. This language is called the instruction set architecture. And of course, you may ask the question, where is this program stored? Turns out that it's stored in the same memory in which the output of the hardware is stored. Okay. The architect is the person who's supposed to be aware of these different viewpoints, and the main goal of the architect is to suggest an ISA. In fact, in the far past, in terms of computer technology, the term architecture and ISA were synonyms. Okay? The ISA should provide support for the users of the ISA. Who's the user of the ISA? Well, these are the programmer, the end user, and even the operating system. All of them are users of the ISA. On the other hand, the ISA should be simple enough so that the hardware designer can come up with an implementation that is not too expensive or slow. So the architect needs to find the balance point between the capabilities of the ISA and the simplicity of the ISA. The capabilities are important because the users need these capabilities. The simplicity is important because we want to make the hardware designer's life reasonable. Okay? So, what exactly is the ISA? It's a specification of the microprocessor from the programmer's point of view. What do we mean here by programmer? This is not the C programmer. This is not a programmer that is programming in a high-level language. Instead, this is a programmer programming in machine language. Okay, so this is the point of view of a very special programmer. In fact, this programmer is no longer a person. Okay, it is not common for people to write programs in machine language anymore. This was perhaps true in the 60s and the 70s of the previous century. People do not do that usually anymore. The machine language programmer these days is a program by itself. Okay, let's elaborate on this. Okay, so let's describe two programs. One is called the compiler and the other one is called an assembler. and try to explain what these programs do. Okay, so I write programs, say, in C, and I want to execute them on my computer, but my computer can only execute programs in machine language. So I need to find a way to translate this C program to a program in machine language. This translation takes part in two stages. In the first stage, I translate the C program to another program in a language called assembly. This translation is executed by the compiler. Okay? So the compiler accepts as input a program in C or in a high-level language and outputs a program in assembly language. This program written in assembly is input to a program called the assembler. The assembler translates the program in assembly language to machine language. So we have a two-stage transformation. Now, what is important to understand is that assembly is not necessarily dependent on the computer on which I am running my programs. So the assembly doesn't perhaps know yet, so to speak, what is going to be my ISA. Okay? So this part, the compiler part, doesn't depend on the type of computer on which, does not need to depend on the type of computer on which you're going to execute your machine language program, because the dependency on the machine itself, on the actual ISA, is in the assembler. The compiler part is, architecture independent. Okay, good. Having established this point, we see that this two-stage sequence of translations that starts with the C program and ends with a machine language program has a few advantages. The microprocessor executes programs written in a very simple language, the machine language. This is important because it makes the task of designing the microprocessor easier. The C programmer doesn't need to think about the actual platform that executes the program. There's only one compiler that you need to write, and then for each platform, by platform I mean ISA, for each instruction set architecture, there's an assembler that translates the assembly programs to the machine language of the platform. Every stage of this translation works in a certain abstraction. The amount of detail increases as one descends to a lower level abstraction. In each translation step, decisions can be made that are suited to the current abstraction. Okay? So this is important, that we partition the task into parts which are small and well defined, so that fulfilling this task is not too hard. Okay, now of course, what I just described here gives rise to two questions. And the first question, who compiles the compiler? Because the compiler is a program that runs on the computer, and the computer can only execute programs in machine language. So who compiles the compiler? And the same question, or I should say here, who assembles? And the same question pertains to the assembler. Who assembles the assembler? Who translates the assembler from assembly language to machine language? Okay? So these are cute riddles. I'll leave them open. What is the instruction set, or the instruction set architecture? It is the machine language of the processor. In general, a machine language has very few rules and very, very simple syntax. In the case of the specific ISA, which I'm going to explain in this chapter, every sequence of instructions constitutes a legal program. Now, this would not be, of course, the case in high-level programs where the syntax has lots of rules and it's very rich. Here, the syntax is very primitive. This explains why we call machine language a set of instructions, because any sequence of instructions is a valid program. Okay, let's start to explain what the main memory is, because it is a major component in the design of a computer. The main memory is used to store both the program itself, namely the instructions, the machine language instructions, and the data, namely the constants and the variables that are used by the program. I'll elaborate on this issue shortly. We regard the memory as an array of words where each element in this array holds one word. The memory, the main memory, is nothing but a RAM that we saw in our chapter on synchronous circuits. This means that the processor can access the memory in one of two ways. It can either store a value, a word, in the array, or it can read the value that is already stored in the array. Okay? Now, I want to emphasize that the memory is used for storing both the program and the data. Okay? Now, this is not such a trivial issue. Okay? So I'll give you a trivia question. Who was the first person who suggested to store the machine language program in the main memory of the computer? Up to this suggestion, the main memory was used only for storing the data, not for storing the program. Okay. Who was the person who suggested it? When did that happen? Okay. So now let's elaborate on a read and a write operation with regard to the microprocessor and the memory. So here we have our memory. It is an array of words, and we want to read the contents of MI. We have a special register called the MDR, Memory Data Register. The Memory Data Register, what it does is when you want to read MI, you access the ith word in your memory array, and you copy the contents that is stored over here into the MDR. When you want to write, you just reverse the arrow. Instead of going from MI to the MDR, you copy the contents of the MDR and you store it in MI, in the ith entry in your array. Okay, so now of course the question arises, where is I stored? By I mean the index or the address in the memory that you want to access. Okay, for this purpose we want to introduce two special registers. The first register is the MDR, we talked about it, and the second register is the MAR, or MAR, stands for Memory Address Register. Now, what you do is you store the index of the memory cell that you want to access in the MAR. In a read operation, this is a write operation, in a write operation, the MAR stores this index, and you take the contents of the MDR and you write its contents in the index, which is pointed to by the MAR. Now, the MAR points indices in binary representation. This is why we have rectangular brackets around the MAR. In a read operation, the MAR again gives us the index of the memory entry that we want to access, and we take the contents of the word that is stored there and we copy it to the MDR. So we have two special registers that serve as the interface between the CPU, the computer, the microprocessor, which is not depicted over here, and the memory. This is the memory. And the memory. This is the memory. Very good. Okay. In a read operation, we need to compute the address that we want to access and store it in the MAR. We need to copy the contents of the accessed word in the memory to the MDR, and then finally we copy the contents of the MDR to another register called a general purpose register. Okay? So the MDR stands between the general purpose register and the memory. From the point of view of the memory, the interaction with the microprocessor is only via the MAR and the MDR. This is a neat description, but it is incorrect when we're dealing with the case of reading instructions, because I said before that the main memory is used for storing both data and the instructions of the program. So when you want to read the instructions of the program, you do not use the MAR to determine the address or the index that you want to read. Instead, you use another special register that is called the PC, the program counter. And then when you want to read an instruction, you copy the contents of the memory in the index, which is represented by the PC, in another special register called the instruction register. So the PC is analogous to the MAR, and the IR is analogous to the MDR. The only difference is that the PC and the IR are special registers that are used for accessing instructions, whereas MAR and MDR are special registers that are used for accessing data. So reading data is different from reading instructions because the address in data is given by the MAR, the address in instructions is given by the PC. What you read from the memory is stored in the MDR when it's data, and it's stored in the IR when it is an instruction. Now we have registers that serve as the working space of the microprocessors. We have three main types. We have the PC and the IR that we spoke about, the program counter and the instruction register. We have the MAR and the MDR that we also spoke about. These are the interface with the main memory for the purpose of data. And on top of that, we have the GPR. The GPR is a general purpose registers. These are the scratch pad of the microprocessor. So let's summarize. In the DLX, in the simplified DLX, we have architectural registers, all of which are 32 bits wide, and here they are. We have 32 general purpose registers called the GPRs. Sometimes you call this the file register. It's another name for the GPRs. 32 general purpose registers. They are called R0 to R31. R0 is an exception. It cannot be, you cannot write to it, you can only read from it, and it always stores the all zeros vector. It cannot be modified. All the others, R1 to R31, can be modified and store any 32-bit wide word. The program counter stores the current address of the instruction that is being executed. The instruction register stores the current instruction, namely IR is a copy of what is in the memory in the address given by the PC. And we have the special registers MAR and MDR that we elaborated on previously. So let's see an example of how the GPR interacts with the memory and how things work. So instructions are separated to memory accesses and computations. The arguments and the results of computations are stored in GPRs. So let's look at an example in which I have a high-level instruction which says Z gets the value of X plus Y. How is such an instruction executed? Let's see it by a diagram. This is my memory. In M1 I store X, in M2 I store Y, in M3 I store Z. This is of course completely arbitrary. The entity which makes this decision what is the address in which variables are stored in is the compiler, but you won't get into that at this moment. So let's assume that X is stored in M1, Y is stored in M2, Z is stored in M3. And we want to compute Z gets the value of X plus Y. So the first thing we need to do is we need to read X and store it in a GPR. So these are my GPRs. Let's say I use R1 to store X. So I need to load M1 to R1. Okay? This is of course done by taking the address 1, storing it in the MAR, performing a read instruction on the memory. The read copies the contents of X to the MDR, and then we need to copy the MDR into R1. This is not depicted in this figure. Next, we need to copy Y to R2. That is loading M2 to R2. So now X is stored in R1, Y is stored in R2. Now we need to perform the addition. We perform the addition, we feed an adder with the values of R1 and R2, and the sum is stored in R3. Now we need to copy the sum back to the memory. So we need to store R3 in the location M3. Okay, good. The instructions in the simplified DLX come in two types. There is the I type and the R type. Each instruction is 32 bits long. Always. Now, the partitioning of these 32 bits into fields is different in the case of an I-type instruction and in the case of an R-type instruction. In the case of an I-type instruction, these are bits 0 up to 31, I should emphasize. In the I-type instruction, the last 6 bits encode the instruction, whether it is an add instruction or another instruction. We'll talk about the type of instructions that you have in I-type. The next 5 bits are devoted to storing an index of a GPR. So we know that there are 32 GPRs, R0 to R31. So an index of a GPR, Ri, can be represented using 5 bits, right? Because 2 to the power of 5 is 32, right? So these 5 bits are an index, Ri. There are the index I of a GPR, which is either R0, R1, R2, up to R31. This is this field. This will be an argument. This is an argument. The next 5 bits are the destination. These are the register in which you store the outcome of the instruction. And the first 16 bits, the rightmost 16 bits, are an immediate. This is a constant, 16 bits of a constant that appears as part of the instruction itself. The R type has 2 fields for the operation, for the encoding of the operation, the last 6 bits and the first 6 bits. The last 6 bits indicate I am an R-type instruction, and the first 6 bits, the field called the function, indicates what instruction you have here. And the separation into fields is a little bit different. We have 5 bits for RS1, 5 bits for RS2, 5 bits for RD, and these 5 bits are not used. Not used. Okay? Now, RS1 and RS2 are the 2 indices of the operands of the instruction that you're going to execute in R-type. RD is the index in which you want to store the result. Okay, so RD here and RD here mean the same thing. This is the index of the GPR in which you want to store the results. RS1 and RS1 here mean the same thing. This is the index of the GPR from which you take the first argument, and the immediate will be the second argument in an I-type instruction. RS2 will be the index of the GPR that holds the second operand in an R-type. Okay, let's start going over the type of instructions that we have in a GPR. We will do this in the second part of this chapter. Thank you.